So far in 0005 we discussed propositional calculus, which is a really useful tool, but has some limitations. Specifically, there are a lot of mathematical statements which we'd like to analyse from a logical point of view, but which don't fit well into the framework of propositional calculus. So here's some examples to show the limitations of propositional calculus. It can't express statements like, there exists a rational number x with x squared equal to 2. Or, for all natural numbers n, there exists a natural number m with n greater than m. Or, for all real numbers m, there exists a real number n, such that for all real numbers x, if x is greater than or equal to n, then e to the power x is greater than or equal to m. Now, these kind of statements are extremely common in mathematics, especially in the study of analysis. You'll recognize all these kind of statements from your mathematical analysis course. And they don't fit well into propositional calculus. So, in order to study these, what we need is something else, and that something else is called first-order logic. You'll sometimes see this called prepositional calculus, but that's just too confusing for me, so I'm going to refer to the kind of logic we're now going to be studying solely as first-order logic. So when we defined well-formed formulas in propositional calculus, what we were able to do was to give a very precise, rigorous definition of a well-formed formula. We set up our language, and our language consisted of symbols for propositional variables, logical connectives, brackets, and that's it. And then we were then able to give a rigorous definition of what formed a legitimate formula in this language. In other words, what is a well-formed formula. The corresponding definition of what is a legitimate formula of first-order logic is much more complicated, and we are not going to give a full, rigorous definition of what is a legitimate first-order formula. Instead, we'll be content with studying some examples of first-order formulas. If you do want to know the precise definition of what makes a legitimate first-order formula or not, you can take MATH0037 in your third year, or if you can't wait that long to know, you can read, for example, Derek Galbraith's book on propositional and predicate calculus. So as I said, instead what we're going to do is simply look at examples of first-order formulas and look at how to interpret those, how to understand them, how to determine in a particular interpretation whether or not they're true or false. So here is some examples of first-order formulas corresponding to our statements on the previous slide. So first of all, here is the statement, there exists x, p of x. So here, p of x represents some relation that might be true or false for some variable x. And that corresponds to the statement on the previous slide, which we wrote in informal English language. There exists a rational number such that a particular property of that rational number holds, x squared equals 2. So of course that's a false statement. Just as well-formed formulas can be true or false, our first-order formulas, once we interpret them in some way, will also be able to be either true or false statements. The next statement we wrote on the previous slide was that for every natural number n, there exists a natural number m with n greater than m. And that corresponds to a first-order formula here, saying for all n exists m, p, n, m. And again, the function of this p, n, m thing here is it's a relation, or it will be interpreted as a relation between the variables n and m. And finally, the most complicated statement on the previous slide was that for all real numbers m, there existed a real number n, such that for all real numbers x greater than or equal to n, e to the x was larger than m. And you can express that by using the final example first-order formula here, where we have two relations, p and q. So the really new feature of these first order formulas is the presence of these things which look like an upside down A and a backwards E. Those things are called quantifiers, and the way we read them and the way we interpret them is that the upside down A here is read as the words for all, and the backwards E here is read as there exists. So you should think of these first order formulas as being like well-formed formulas. They're things which aren't in themselves true or false, but which become true or false once you interpret them in a particular way. And the way in which we performed an interpretation of a well-formed formula was to take the propositional variables in that well-formed formula and to decide whether those propositional variables were true or false using a truth assignment. But for first order formulas, the problem of interpreting them and then deciding whether the interpretation is true or false becomes more complicated, because in first order formulas we have things like these x and n and m which are variables, and we have to decide where those variables come from, and we also have to decide on the meaning of these things p and q, which get interpreted as relations. So that's going to be the subject of the next video, but for now I just want to summarize what first order formulas are made up of. So first order formulas consist of, first of all, quantifiers for all and there exists, written as this upside down A and backwards E. Next, the logical connectives and brackets, which you're already familiar with from well-formed formulas. Next, which is new, variable symbols, which typically we write as lowercase English letters. So variable symbols are not the same as propositional variables. Variable symbols are not things which are true or false. Those are things which might be interpreted, for example, as real numbers, or as natural numbers, or as integers, or as elements of some other set. And the final ingredient in our first order formulas is relation symbols, which we typically write as capital English letters. So in the example formula, which you saw on the last slide, here we have some quantifiers for all and exists, and the statement will be read out loud and interpreted as saying for all m there exists an n such that for all x something happens. You can see also that there are some logical connectives. In fact, there is an implies connective there. There are some variable symbols. The variables involved here are m, n, and x, and those variable symbols also appear in the rest of that formula. And there are some relation symbols. So the relation symbols present here are, there is a p and a q. And there's a relation p and a relation q.